Passable.
All right. At least I noticed one student that was not here on Thursday, so we have to repeat. I was hoping there would be more students that were not here on Thursday, but so anyways, we were trying to discuss some details and definitions on what we call the state space model, which is a standard model for dynamical systems. And the schematic, a probabilistic graphical model basically for the state space model, for those who are not here, it looks basically like that. x1, x2, xn are the states, let's say at time t1, t2, tn. And the states are hidden variables. We don't have access to them, so we cannot measure them. But we have some observations, y1, y2, yn. You can interpret for now that y1, y2, yn are basically some noisy observations of the state. So the idea is to estimate the state from the y's and to do it sequentially in a way that is scalable, so that the cost doesn't increase as we increase that. So this is a very universal problem for anybody who works on anything that has to do with dynamical systems. This is the starting point. But as I mentioned on Thursday, the things we're going to do with sequential Monte Carlo in the context of this problem don't have to necessarily be applied only to dynamical problems. So if you use your imagination, you can make any problem to look like this, okay? And so there is absolutely no way you can escape from state space models if you do anything in the context of time-dependent dynamical systems. All right, so some definitions of distributions. So we need to do two things. This is the dynamics of the model. Basically tell us how to sample state x1 if we know state xn minus 1. So this is a Markovian model. It only depends on xn minus 1. And that's, you can call this the transition model or the dynamical model. It tells you how to go from x minus 1 to xn. You notice this doesn't depend on time, right, the way we have it. And also we provide a distribution to sample the initial state, okay? So if we go back, we're giving a law, if you like, on how to go from x1 to x2, from x2 to x3, etc. And then we have also an observation model that tell us that at each time, yn depends only on xn, and this is the distribution that defines the observations. Think of this as the likelihood model. Okay? So you notice, again, yn depends only on xn. So y1 depends only on x1, that's why you see these errors here. y2 depends on x2, and because of this conditional independence relations given the x's, the likelihood, you can write it, if you have, let's say, observations y1 to n up to time n, this distribution given the x's can be factorized basically as the product of these g's yi given xi. So the problem of interest is compute the states xn given yn for n equal 1, 2, 3, etc. in a way that the calculations don't blow up. Don't have time to review any of these things again, so I'm going to assume that you read them. So let me see what slide was that, 14? 21. All right, so the objective for the lecture today, and I'm sure the lectures next week, because we will do implementation of this, is to compute this posterior. So compute the probability of the states x from 1 to n, given the observations y from 1 to n. And we're going to have to do this sequentially, all right? N equal to 1, n equal to 2. And the key thing here you observe is that as n changes, the number of arguments in this distribution changes. So it's not like a posterior and some variables that they are fixed. So you start with x1, then it's x1 and x2, x1, x2, x3, etc. So so that's the target distribution, and we really only know this in unnormalized form. So what we need to do is to get this some expression for the unnormalized of this posterior. What we do is we'll write the prior, right? So the prior of the states. This is for the initial state, and this is for the transitions from one state to another, and this is the likelihood. So if you write the product rule basically, and you only take the numerator, the posterior in a normalized way looks like this. Okay? Again, the prior distribution, the transition, and the likelihood, and the normalization factor. And we gave an example where this is, it may be important if you're interested in questions beyond sampling. So the normalizing factor requires a very high dimensional integration, so we need to find ideas that we don't have to do those integrations. Notation, we use the unnormalized, pi is the posterior. This is the notation we use, so this is the posterior. This is really the target, but we only know the unnormalized part, and the unnormalized part is really the joint distribution of x and y, and z is the normalization factor. So I'm going to use this notation gamma n to denote basically this distribution, and Gn to be the normalization factor. All right, we discuss a few interesting recursive equations. So let me find only one of them. All right, so so again, this is what we were interested. Okay, so I gave you lots of 2 or 3 different versions of recursive equations. Recursive means something that you start with n equal 1, and then you use that to update at n equal 2, etc. And so let's take the problem of calculating basically this posterior distribution in a recursive manner. In a recursive manner means calculate this distribution if you know this distribution at time n minus 1, which is this term here. Okay? So if you know this at time n minus 1, what do you need to do to update and compute this distribution at time n? So the algorithm, and we went briefly through the proof that's only on this slide, and involves nothing but the sum and product rules of probability. The idea here is, if you already have this distribution, you do a prediction of the state at xn. And so given the data only up to n minus 1, you can compute this predicted distribution. The only thing you have to do is multiply this with the transition probability that you see there. So once you have, so again, notice this is the distribution of all the states up to n, but given only the data up to n minus 1. So now once you collect the data to time n, you can update this, and the only thing you need to really do, at least in a normalized fashion, is multiply this predictive distribution with the likelihood at time n. Okay? Now if you want the normalization factor as well, it comes to look this complicated term, and this complicated term, as you can see from the derivation here in 2 lines, it requires nothing else but the marginal distribution at n minus 1, so this is the marginal posterior at n minus 1, times the transition model times the likelihood, and integrating xn minus 1 and xn out. So basically, looking at these 2 equations, right, you can start from time 1 and then proceed to time 2 and keep updating these posterior distributions without having to recalculate everything from scratch. Again, this is a forward calculation. You proceed forward in time. So from n minus 1, you do one prediction, and then you do one update, and even the normalization factor can be computed, as you see on this integral, the same fashion. These equations don't come out of nowhere. They are simple examples of the sum and product rule of probability, plus some independence relations implied by the state space model. We did actually some more interesting cases, right? So one of those interesting cases was to define what we call the smoothing distribution. So remind me, what is the filtering distribution? I forgot. Thursday was a century away. What's the filtering distribution? So at any time, let's say at time k, what's the filtering distribution? When I say I don't want a formula, but what do we call a filtering distribution? A little bit louder, I cannot hear.
You mean that you want...
I'm asking what is the definition of the filtering distribution. I see there it says smoothing distribution, and what I'm asking is what did we call a filtering distribution? So at a given time, k, what is the filtering distribution? So for example, on this thing, okay, let me just go. So is this distribution a filtering distribution? So this is here, I only have the marginal. It's the same algorithm as before, but I only work with the marginals. Is this a distribution, a filtering distribution? By definition? Yes, all right, so you should remember that. You know, once upon a time, a student from engineering wanted to take the qualifying exam, and in their course, you can take it using the courses, you know, you can take it on different subjects, and so he wanted to take it on this stuff. And I told him, it's everything, it's open books, open internet, open everything. So I asked 5 questions, such as, what is this and what is that? He had no idea where to even look. I was like, I basically almost, you know, I just couldn't take it. He could not even find in the notes where things are, right? I'm not laughing, it's tragic, right? I don't expect you to know the answers of these things, right? But it helps to get a sense, because in the literature, when they tell you, you know, if you search on Google filtering, effectively what it means, every time you get new data, you update at that instant. So when you collect all the data up to time n, this is your first estimation of xn. Okay, so that we call it the filtering distribution. And the smoothing distribution, it's a little bit more weird, because if you look here, it says find the posterior of xk, where k is way less than n, given all the data up to time n. So the idea here is you collect a lot of data, and you want to go back and update and say something about the effect of all the data on xk when k is less than n. And we call it a smoothing distribution because obviously this will be less, you know, you smooth it, you provide not only data to time k, but data way past k. Okay? So you use the future to update basically the state xk, so this distribution is called a smoothing distribution, but obviously when you do experiments in real life, right? So you are going to have to finish your experiments and then go and compute this, okay? You cannot do this online, so you require to have all the data and then update xk. So again, interestingly enough, there are recursive formulas to actually do this type of updates, and the recursive formulas, the first thing they require is you go from time 1 to time n, and you compute all the filtering distributions. So you notice here, this is the filtering distribution at this time k. And what distribution is this? How do we call that? The what?
Predictive.
That's the predicted distribution, right? So using the data up to time k, you say now, can you go one step ahead and tell me, what xk plus 1 is, but you don't have yet the data at in k plus 1. So you go forward, you compute these distributions, and then interestingly enough, you can compute this smoothing distribution by actually going backwards and using the recursive formula that you see here. And you can see it's backwards because this is the smoothing distribution at step k plus 1 using all the data, and this is the smoothing distribution at time k using all the data, and the rest are basically, this is the filtering distribution, and this is the one-step predicted distribution. So these concepts of going back and forth, they are very standard for these dynamical systems. And as I mentioned, if you ever take a course on probabilistic graphical models, you don't have to remember any of these equations, because all of these equations you can look visually and write them down in terms of message passing in the graph. Okay, they are more or less standard. Now, for those who have seen this, have seen and you forgot about them, it's very possible you have seen the implementation of these equations when all the distributions are Gaussian. Because when all the distributions are Gaussian, at least this forward algorithm, it gives you nothing else but the Kalman filter equations. Okay? But obviously in our cases, we're interested to use these equations when things are non-Gaussian, non-linear, etc. And we did some examples in that context. All right. So no more filtering equations and all of these things. I gave you those for historical reasons. There's a few more slides with some other problems I'm bypassing. So let me go to important sampling. So I'll remind you what is important sampling. Or maybe you remind me, because it's Friday and I need to be very happy on Friday. So remind me, what's important sampling in general? What's the idea? That's what I'm asking. What's the idea of important sampling? Not for dynamical systems, but in general.
You have a proposal density that's easy to sample from.
All right. So we sample from some proposal density, and effectively, to correct that we don't sample from the true distribution, we use some weights, basically. Right?
Yeah.
That's it. Okay. All right, so let me go rapidly because the notation is going to get a little bit more complicated because now we have this dynamical system, right? So I'm going to put a lot of things. So first, a reminder of the classical Monte Carlo type of approximations. If let's say pi is the target distribution, following the previous notation, we only know this up to some normalization factor. So gamma is the anormalized distribution. So if we can sample directly from pi, we approximate this with this empirical measure, right? So all the samples have a weight 1 over n, and we have this delta masses centered on each sample. And if you actually go and approximate expectations, let's say of a function f, instead of using pi, if you use pi hat, this empirical measure, then you get your classical Monte Carlo estimate where the samples are from the true distribution. Okay, that's the Monte Carlo estimate, and I give you the fundamental results from Monte Carlo methods. So this estimator here is unbiased. So if you take its expectation, it comes to be the true expectations of f under pi, and the variance basically it's 1 over n, the true variance. All right, and if you can combine those two if you like, and write them like a central limit type of theorem. Okay. So square root of n, this is the estimator, this is the true mean, and this is a Gaussian, right? So you can see the variance is 1 over n times the true variance there. If you want to do marginalization in Monte Carlo, so if you're not interested in, X is a high dimensional vector, if you're only interested in component P, you can immediately show when you marginalize using this, this empirical measure, actually what you get, imagine, you have this high dimensional X, right? And you have these delta functions center at X where X is high dimensional. If you want the marginal, the only thing you do is you basically keep the delta mass at XP. All right, so the rest basically of the delta functions in the other X variables are integrated out. So marginalization is sort of an immediate thing. You don't need to do anything. All right, so that's Monte Carlo. So here is the idea of important sampling again. The sampling from pi in general is complicated, so we're going to sample from some other distribution Q. Really there are not too many constraints on Q. It just needs, you need to be smart, basically, at least when pi is greater than 0, Q has to be greater than 0. And the key equation effectively is the equation that you see here. We approximate pi as the weights times Q divided by the normalization factor Z of the distribution. This is an obvious equation, right? Because the weights are gamma over Q, so gamma over Q times Q, so you have gamma over Z, which is pi. Okay? Just remember that the weights, the distribution on the top, is the anormalized part of pi. The idea is we don't really know the normalization factor of pi. So W, little w, is gamma over Q. Okay, gamma over Q. All right. So so this is the importance weight. So if we sample from Q, so a Monte Carlo approximation of Q, this Q hat is the standard thing that we saw before. I am using a little bit more rigorous notation here with probability measures, but I will not bother you, so this dx, don't pay attention. Okay, so you have this Monte Carlo approximation for Q, and if you go and plug in that Q inside pi, you're going to get some interesting calculation. So nothing's particular. This was the equation I had before. I plug in instead of Q the approximate measure for Q, and if you do the calculations, what you actually get, the new approximation for pi is these delta masses are the samples that you took from Q, but they're now weighted by capital W, and capital W are the normalized weights. All right, so the capital W, before we had little w, all right, and you notice here is little w divided by the summation of all the w's, so this thing together is capital W. So the only difference really between important sampling and regular Monte Carlo is the samples come from another distribution, not from the actual distribution, and to correct that, element there, you just basically have to put these weights W in front of the empirical measure of pi. So when you can use this to calculate, of course, expectations. I think it's going to be on the next slide. But let me just show you the normalization factor of the distribution. All right. You remember this normalization factor? Okay. How do I get this equation? I'm confused with the notation. Help me. My brain doesn't work all the time properly. I mean, for a moment, all right, don't bother about this hat, okay, because I'm going to use the empirical measure there. So, would you agree with me that the normalization factor is the integral of gamma? All right, so gamma over Q is the weight, okay, and here I am going to take the expectation of the weight, all right, with the empirical measure. All right, so I can use a Monte Carlo approximation. So when you do this, immediately you can see the normalization factor is really nothing else but 1 over n times the summation of the weights. This is a fantastic approximation, right? You can get the normalization factor, which we have discussed in the course, that it's usually very difficult to get, you can actually get it with simple Monte Carlo approximations, and in this case, important sampling, okay? The only thing we do is, you know, we use the empirical measure there for Q, all right? And so if you put this Q to be, you know, 1 over n times this summation of these delta functions, then you get 1 over n times the W's computed at xr's. Okay? So, and the approximation of the distribution pi with important sampling, it looks as we expect, right? These delta functions again, but now you have this normalized weights, right? This is important. These are the normalized weights. I mean, of course, if you don't really care about normalization, you can put any weights there and you're happy. Now, the next slide, I told you when we did important sampling, because we bypassed the proof on this, there is, because of these weights, and because, actually, if I can go back on this calculation, you notice when you find an approximate measure for pi, you do a Monte Carlo approximation of the numerator, and also there is a Monte Carlo approximation of the denominator. So because you have these two ratios of two Monte Carlo approximations, this estimate actually will give you biased calculations. All right, so in summary, if you want to calculate, let's say, with important sampling the expectation, you're going to get summation of the normalized weights times the function at each sample. So in standard Monte Carlo, you have 1 over n, now you have these weights, okay? And it comes out that this estimator is biased, all right? Usually you don't see this in practice, people don't say anything, but because this estimator is the ratio of two estimators, it comes to be biased, and you can see here, the bias is 1 over n times this expectation, okay? So, all the expectations here, the way I wrote them are with respect to the actual true distribution pi, and the variance is the standard variance basically that you get with Monte Carlo, and here there, you know, again, I have the capital W. So that's the new element here, that there is a little bit of bias in important sampling. You can estimate, so the and you know, this bias again, it's I mean, the error, you remember, if you compute approximations like the mean square error for this estimator is bias squared plus variance. So the bias squared is 1 over n squared. So when n is big, the bias is negligible basically, but for small n, this can be significant. All right, I already showed you the approximation for the normalizing factor in terms of the weights. That's extremely powerful calculation. And you can show that the estimator for the normalizing factor is unbiased, and the variance basically is given by this. Okay? So the normalizing factor again is unbiased, and this is actually later in the slides I am using this this variance. What do you need to do to make important sampling to converge? Basically, you need to be sure that the variance of the weights is bounded, and actually, if you can enforce that the weights don't blow up, all right, then you're okay. All right, so this is sort of the key ingredient to make these things to work. All right, now we go to the real problem. We go back to the state space model. So since we review important sampling, let's go back to the real problem. And so I'm not going to do anything new in the next 10 minutes. I am going to give you the same equations, starting with Monte Carlo, then important sampling, but now for our target distribution that looks like this. So I'm going to basically cut and paste the same equations, but I am going to adjust all the notation to this target distribution. So this is the posterior, and we only know this is our gamma. This is the normalizing factor, okay? So the same equations, all right, but now x has n components. So if you do classical Monte Carlo, would you agree with me that this is the approximation, the empirical measure of the target distribution? right? Nothing has changed. I haven't done anything fancy. So the samples are from the true distribution, okay? And so you have these delta functions in these n variables, and so that's the Monte Carlo approximation. And obviously, if you want to calculate expectations of any functions, phi of the n variables, this is your standard Monte Carlo estimate, nothing new. I literally cut and pasted the equations because it's important to get used to the notation here. There is nothing new, right? I'm not suggesting that you'll be able to do this with Monte Carlo or important sampling, right? But we need to motivate why we're going to do something different for the state space model. I mean, when I say here, take the samples from this distribution, you're not going to be able to keep doing this forever, because this is going to be, how are you going to be sampling thousands of variables and then 1,001 and then 1,002 every time again and again? So this is not, it doesn't seem it's going to be practical. All right? And again, the same questions as before, right? If you write the central limit theorem, the estimator is unbiased and the variance is 1 over n times the true variance. Okay? Nothing, it's the same equation literally as before. What is new is the notation for the particular target distribution. All right, and I remind you, if you want to get the marginal distributions, the only thing, so if you're interested, so when we computed the filtering distribution, but you only want to keep the component xk, then basically everything else is marginalized because integrals of delta functions give you 1, so you only get the delta function center on xk. Okay? So we want basically to find something smarter to do, something that keeps the computational cost fixed at each step n. So it would be interesting if we can approximate this target distribution, right, with the same cost at time 1 as at time 1,000. All right, if we can do this, then we will not have any issues with any complexities arising from this target distribution. All right, so we're going to do important sampling. So I'm going to give you the same equations I had before, okay, the same equations, cut and paste. So we're going to introduce an important sampling distribution Q, all right? By the way, the notation here, just to explain a little bit, Q is a distribution of the variables x1 to xn. So when I say here, given y1 to n, I want to imply that you may want to, in deriving some optimal distribution Q, right, you may want to take account the fact that you actually have some measurements. I'm not suggesting that that is going to be easy, but I want to remind you that you can use the y's in designing this Q of x. Okay? And we will see how that happens. So interpret this, even though we're interested on Q of x, right? The implication here is we can use the information about the y's. All right, so in important sampling, I remind you, this is our target distribution, and you remember we wrote it W times Q divided by this integral. It's exactly the same equation. I just plug in W and Q explicitly, so it looks nice. Okay, so there's nothing fancy. You may be lost looking at this. All right. So what is this equation? So you guys tell me the top equation. What is that? What's the idea here? Read the whole equation. Tell me what it is. We're trying to show the equations for the generic importance sampling. So what's the equation on the top? I am sampling for the important distribution. And what is this? It's the Monte Carlo approximation. It's the empirical measure of Q, right? You need to learn names, right? Because, if you're going to write more a paper, you're going to have to say, this is the empirical distribution of Q, right? It's an approximation defined in terms of particles. All right? So this is, this is the Monte Carlo approximation, if you like, of Q. And if you plug in this Q in the equation I had for pi, for the target distribution, you can get actually an empirical measure for the target distribution, and the empirical measure, it's actually this nice equation there. Will you agree with me? So you basically have these delta masses at the sample sex, and the sample sex are from Q, but you weight them with W. Same equation as before, nothing new. Right? These are the delta functions, right? So I use for samples capital X, that's the notation, all right? Little x are my variables. So I put these delta masses at these samples from the distribution Q, and then I have these weights Wn, all right? And these weights are basically normalized weights that you see there. I remind you that little w is nothing else but the ratio of the normalized distribution with these arguments divided by the Q distribution computed at these arguments. Okay? And again, if you want to approximate the marginal, it's nothing else, all right, but summation of the weights divided by n. This, again, trust me, if you want to do model evaluation or model comparison with Monte Carlo methods, this is fantastic. Can you imagine not having to compute the evidence and you just sample, takes the samples and you compute the weights and 1/n sum of the weights gives you this? It's fantastic. Okay? A very nice, very easy type of calculation. All right? So this is what I was just telling you with words. Obviously, what I have given you is not going to be very helpful right up now, because repeating this calculation and and saying, so when you say take the samples, it's like, thank you very much, because as n increases, how am I doing this? I mean, this is mission impossible. The cost will keep increasing as n increases. So this is not very helpful. It's not very helpful for our objective. This is not going to be a practical algorithm. Not to mention that the variance of the weights may increase and actually exponentially with time. Okay? So when are we supposed to finish the class? At 12:20? Okay. So at least I'll give you a summary of what the idea is, and if we miss something, I can come back and cover it on all right. Okay. So, and again, these are the same equations that I was telling you, that this important sampling estimator basically has a bias, and I'm writing actually this bias here explicitly. You remember the bias is 1/n times the expectation of this times the weights with respect to pi. So you see this explicitly here, okay? And again, the bias in the context of calculating error, it's relatively negligible if n is large. All right. Let me just, before I go to the actual algorithm, right, let me say the following. When you use important sampling, your type of calculations, and we take, let's say, n samples, the equivalent, so let's say you take n samples, all right, those n samples, all right, they are not equivalent, if you like, with n, unweighted samples that you get with standard Monte Carlo. So effectively, the effective sample size is n divided by 1 plus the variance of the weights. Right? This is a very important sort of formula that we need to use in practice. So if let's say you calculate some expectations and you have some approximation of some quantities, and you do Monte Carlo and you use 1,000 samples and you say, oh, this is a very good estimate. Well, when you use important sampling, it's not going to be the effective number of samples. It's not going to be 1,000, but it's going to be 1,000 divided by 1 plus the variance of the weights. All right? So as the variance of the weights increases, all right, the number of effective samples is actually becoming smaller and smaller, so that's not very good. And in practice, a good way to keep track of the effective number of samples is this quantity that you see here. If you publish anything in any paper that you do Monte Carlo with important sampling, you basically have to report this, what is called the effective sample size. And the effective sample size is basically the summation of the weight square inverse, okay? And you can appreciate what this is all about by taking two limiting cases. In one case, let's say that all the weights, they are equal and equal to 1 over n. So if this is 1 over n, so you have 1 over n squared times n, you get 1 over n, so the effective sample size is equal to n. So this is ideal, it's right, like running regular Monte Carlo. But if, let's say, in the worst case, one of the weights is 1 and everything else is 0, then the effective sample size is the worst, is equal to 1. So you may be taking 1,000 samples, but really only one sample contributes to effectively to the calculations. So it's good to keep this thing under control when you do important sampling, that somehow the algorithm does not deteriorate. The highest is, the better, right? This is the effective sample size. All right, so let me go to the real problem. And give you some, what's the idea? Okay, we have 10 minutes, so let's do our best. Here is the idea. Let's say at time n minus 1, we compute some important sampling approximation of the target distribution, all right? In the generic thing that I showed you before, I never use the distribution again. So, when I go to calculate Pn, I start doing all the calculations from scratch. So here is the key ingredient of sequential important sampling. Can somehow reuse this information of pi n minus 1 to compute pi n. So rather than wasting all the effort in computing pi n minus 1, can I reuse that information to compute pi n? So the idea here is, even though pi n has more variables, somehow this distribution is not very much different from pi n, all right? So can we use this information to actually compute effectively, efficiently pi n? So let me start the algorithm just to give you, a sense of how things may work. So let's say we start at time 1. This is our target distribution, right? We're going to do important sampling. So we're not going to sample from here, but we're going to sample from some importance, distribution Q1. So we take samples from Q1, and then the approximation of pi n. This is the normalized posterior, looks like this, and the approximation of the normalization factor looks like that. I want you to look at these equations. There's nothing there. It's a repeat of the equations from before. But tell me that these equations make sense. So this is at time 1. I haven't done anything fancy. I only sample from an importance distribution Q1, and then my approximation for my target distribution is this delta masses weighted by the normalized weights, and similarly the approximation for my normalizing factor is the sum of the weights divided by 1. Is that okay? Right? That's time 1. All right, so let's do this time 2. Let's do something smart at time 2. All right? We are going to do something smart at time 2. Before, we were sampling from a proposal distribution Q2 of x12 given y12. So now I'm going to select a proposal distribution that has the following form. So look at it and tell me, why is this interesting? I mean, I can use anything I want, so I'm going to use this. What's the idea here? Look carefully on the first term on the right-hand side and tell me, why is this of interest?
This one just calculated in previous step.
you remember x1 was sampled from this distribution, Q1. So I don't have to update x1. And for that x1, the only thing I have to update is x2 from this incremental term that we see here. Make sense? All right, Q1, I mean x1 does not have to be updated because we sample it from this distribution, and given that x1, I have to sample x2. So you know what you can think because this is a dynamical problem, think you sample x1, and then you take that sample x1 and you move it forward in time. That's why this method is called a particle method, right? It's like you have particles that move, in space. So x1 is moving to x2 with this incremental proposal distribution. So this is what I just said. If you already sample in the step 1 capital of x1, then effectively you're moving this to x2 given x1 using this term. And of course the index here I is the number of samples, right? You will take several samples x1, and then each of them you move it to x2 through this Q2. And you may say, and so, but what are the weights? Well, let's see. Are the weights actually easy to compute? So what's the definition of the weights? Will you agree with me that the definition of the weights is at time 2 it's the anormalized posterior, that's the target distribution, divided by the proposal distribution, which is this, all right? And then what I do is I multiply and divide by the target distribution of time 1. And then what is P of x1, y1 divided by Q1 of x1, y1 is my weight from step 1. Right, this is the weight from step 1. And then I have some incremental weight that looks a little bit complicated right now. But we can simplify, because for the state space model, I can actually tell you right away the ratio of this joint divided by this joint at time 1, it only involves the transition model from x1 to x2 and the observation model of z of y2 given x2. So the ratio of these two things is very simplified. Okay? So the idea here is the weights are updated. We don't waste what we computed, we keep it. So the previous weight is updated with these terms to give us the new weight. There is no recalculation. And can we do this for all time steps? Yes. So here's the idea. We're going to approximate this proposal distribution is going to look like this. So the Qn is going to be the previous proposal distribution Qn minus 1, and then Qn is going to give us xn for each of the particles we sample up to time n minus 1. So you can write this in a product form like this, okay? And all right. So the idea is, if we had computed the representation, the particles at time n minus 1, we have various particles high, then effectively we only need to sample this term Qn to move these particles forward to time n. All right? So the idea is all of these particles are being reused. Nothing is wasted. The only thing I need to actually is to compute xn of I. Okay. So the incremental weights from n minus 1 to n, they look, that's the previous equation I had from step 1 to 2. All right, so this is the incremental weight. And all right, and I already told you this divided by that for the state space models is nothing else but the transition probability plus the observation model, okay, divided by Qn. All right, so this is extremely simple question, and the only thing I have to tell you is, can we actually simplify this Qn to make life and implementations much easier? Okay, so because I only have 1 minute left, so let me tell you how we can actually simplify if I can find it. Here's the answer. So we're going to make the calculation of xn to only depend on the previous xn minus 1 and yn. So in other ways, before, if you remember, All right? There was dependence from all the data up to time n, and depend from all the particles from 1 to n minus 1. And now we're going to say, nope, let's use only the previous xn minus 1, and let's use the current data point yn. And if you think about it, it makes sense, right? Because if I know the state xn minus 1, that includes everything about the data I collected up to time n minus 1, all right? So I don't really need to keep track of that because of conditional independence. So Qn basically can be function well only as a function of yn and xn minus 1. So again, if you do this, this is how basically the weights will look like. These are the weights at the previous time, and these are the incremental weights that have extremely simple evaluation of the dynamical model and the observation system, and then a proposal distribution that looks very simple like this. So the different algorithms that we will discuss next week, and there are hundreds of those, is what actually do you use for this proposal distribution there? Depending on what you use, you get something that looks extremely trivial and you can program in 1 line, or something that you can program in 2 lines. Really, these algorithms are extremely simple to program and they scale very well. You just need to be careful that you understand what is going on. All right, so I will finish there and we'll pick it up and we will do lots of examples. And you're going to have to program some of these things as well as part of for the forthcoming project. Okay, homework too. All right.